So now that we have these columns, the columns that through exploratory data analysis that we've determined would most likely predict an accurate price value, we can save this into data. So let's create a data variable. Now this is our data that we're going to be using for our model. And now using our sample, let's create our data split. We learn how to do this in the data preprocessing section. And we're creating data split from the data set, but we're going to be using stratified sampling on the price column. This tells our sample to sample or when it's randomly picking rows from the data set put into test and training data sets to evenly select or to follow what's called stratified sampling within the price column so that it gives a more balanced sample. Okay. Now this goes into statistics and probability and sampling and that kind of stuff. So I'm not going to go into too much detail, but this is generally good practice to do that, to provide the output variable as input to the strata parameter to allow for stratified sampling on that column, because that's the column we want to predict, and we don't want a skewed or an imbalanced sample to train on or to even test on. So let's create our training data set. Training data split, and then the testing would be like this. So now if we run this, we have a training data set of almost 40,500 observations, and then we have a test data set of almost 13,500. So remember, by default, I think this gives us a 70 initial split. I think it's a 70-30 or a 75-25. Yeah, it's a 75-25 split. Okay, and that you can adjust that if you want to, but there's no need to. So now let's build our model just using the built-in linear model function in R, and we're specifying the price as the outcome variable, and then all the rest of the variables as the input variables. And the data we're going to be building our model on is the training data set. So there we go, we built our model. Now we can view our results by using the built-in summary function, and this gives us a summary like this. And there's a lot of information here, and a lot of this we haven't covered because it requires some very detailed statistical knowledge, like what a t-value is and that kind of stuff, and the f statistic, and we're going to be covering some of these actually in the following sections for logistic regression and that kind of stuff. But you might notice r squared. So this is the goodness of fit function. Remember how well the model represents, in this case, our training data set, because we haven't validated this on a test data set yet. So this is a pretty high value. This means that this model is pretty good, right? It means it pretty accurately describes the training data set. And then we have the p-values. Remember, we said that if the p-value is less than 0.05, then we can reject the null hypothesis. And the null hypothesis was the assumption that there is no relationship between these variables and the price variable. So by rejecting that, we're saying that yes, there is a relationship between these variables and the price variable. So this is a good sign, right? Because, you know, this is a very small value. So this means that there's definitely a relationship between those, the input variables and the output variable. So feel free to search more about interpreting these results. But remember how I said that every function and every package in R that does, you know, machine learning or implements machine learning algorithms have their own approach. This is the way that the LM summarizes its results, and another function might summarize its results in a different way. So what the Broom package allows us to do is, I just got to make sure that if we have Broom installed, and we do. So what the Broom package does is it gives us a function called tidy, which actually universalizes the format in which these machine learning algorithms present the results. So if we were to, instead of using summary, to use tidy from Broom on our result, we would get a data frame. And this is very, very nice because we can now use this as input, right, into other functions and that kind of stuff, because it's very easy to work with. This, we can't work with it, right? We can't extract anything. Here we can extract whatever we want. So, we have the standard error and the p-value, and you can see that the p-value for all of them is way below 0.05, like orders of magnitude below, which is a good sign. Now, this is how you would train a model and how you would use a core package. We can repeat everything we just did without selecting these columns. So let's actually just keep all the columns there. Okay, so let's define data as all, the whole diamonds data set, and then let's do the splitting again, and then let's train the model. Now let's view another. This is the old original summary, and then we can do the new summary, and then summary model. And here you can see that now we have all the variables, and what's been done is these have actually been converted to dummy variables. So new variables have been created. Remember how we did this in the pre-processing step, where we vectorized or encoded categorical variables into multiple columns. So instead of having one column with L, Q, C, 4, 5, 6, we created 6 different columns, and with either 1 or a 0 corresponding to if they're L, Q, C, 4, 5, or 6. So LM does this in the background on its own, so it normalizes, it vectorizes the variables, and it should actually normalize them as well, if I'm not mistaken. But now we have a more accurate model. As you can see, we have a higher R-squared value, and we should have, so the more, it's not always the case, but in this case, the more variables we provided, the better the model should have turned out. And you can also see the correlation or the significance code. So, something's highly significant or not based on the number of stars that are next to each variable. So you can see that, for example, Z and Y seem to be highly significant. So again, I don't want to get into too much detail, but this column essentially gives the p-value of each variable to the outcome. So the significance of that variable in the outcome and how much it plays a role in it. So this is a legend, right? So remember how we said that p-values less than 0.05 are significant, and the smaller the value, the more significant it is. So essentially, if the p-value is less than 0.05, it'll have 1 star next to it, and that means that it's significant. It does play an important role in predicting the outcome variable, okay? And if it gets more significant, it gets more stars. So as it goes down to 0, which is very small, it gets more stars. And if it goes above 0.5, it becomes a dot, and then it just becomes a space. So what's interesting here to observe is that when we just had those 3 variables or those 4 variables down here, obviously they were all significant in determining the outcome. But when we put in all the variables, you all of a sudden you see that X, Z, and Y don't really play that big of a role in predicting the outcome variable. They're less significant, though they're not insignificant. So they're still, they are insignificant. So you can assume that they're insignificant. This is more significant, but you can just ignore these variables basically and focus just on the ones that have stars. So all of these other variables seem to play a big role in determining the outcome variable. This one, for example, more so because it has 2 stars, or this one less so, I'm sorry, because it's 2 stars. This one doesn't because it has no stars, so on and so forth. So, this should give you just a very quick understanding and quick glance at the variable importance and which variables play a more important role in determining the outcome, that kind of stuff. But again, this does require some knowledge to interpret. But in general, we're content. We like the results. So, we don't really need to delve further into the details. Now let's redo all of this using tidy models. So let's create our data split. Let's do this again, but just on the data, on the diamonds data set. Oh, by the way, now we can also create, so this was the original summary, and we can create the new summary based on just the diamonds. New summary. So broom tidy model, and there we go. Now we have, all the other variables are included, and we can view in detail the p-value of everything. We can sort this by p-value, and so we can see that these terms play the most significant role in predicting the outcome, which is very contrary to what we discovered using the correlations, right? So that's very interesting, and the reason for that is because we ran the correlations on just the numeric variables, right? We didn't include the categorical variables. In fact, we explicitly removed them. So if we had included the categorical variables, and in fact, if we had vectorized them, so we had created new categorical variables from the existing categorical variables, we would have found that they have a higher correlation to the price than X, Y, and Z. So this is something, this is a good lesson to keep in mind, that you have to really make sure that you're looking into everything, and not going on certain assumptions and therefore losing sight of some other possibilities that might exist. So this is very interesting, right? It's very good to see this, right? X is all the way down here. Even though X is very significant in determining the price, before we get to X, there are all these other variables that play a bigger role and that are more significant. So don't exclude categorical variables just because you're predicting a numeric outcome, right? I showed you guys how to convert categorical variables into numeric variables. So you know how you vectorize it and then normalize it. So there's no excuse to do that. Don't bias your data based on assumptions that you might have. So having said that, let's go into the tidy models approach. The tidy models approach. So we can create our split, our testing and training data split on the diamonds data set directly. Okay. So we do that. And then let's pre-process the data. And so let's take our training data. Let's create a recipe. And in this recipe, let's specify the outcome variable to be the price and the input variables to be everything else. And the data that we're using is the training data set. And then we can vectorize all the categorical variables. So all nominal variables can be vectorized. So remember, the step in recipes that vectorizes or encodes categorical variables is called dummy, because you're creating dummy variables. So the step that creates dummy variables. And then we can normalize all our numeric variables. And now remember, after this step, all our variables are numeric because we've converted all the categorical variables into numeric variables. So essentially here we're picking all the variables, but we want to exclude the outcome variable, which is the price variable. And then we prep this recipe. What's going on? This will equal in step dummy all nominal. Oh, so we want to exclude it. So with that minus sign, okay. Run that. We have our recipe. So training data contains this many data points and there's no missing data. We created dummy variables from cut, color, and clarity. And then we centered and scaled for caret, cut, table, XYZ, and cut 1, cut 2, cut 3, cut 4, and color 1, color 2, etc. Those are all the numerical variables that have been created from cut and color and clarity due to this step dummy. So that's why order is important, right? If we had done the normalization step first, then only the numeric columns would have been normalized, and then we would have created new numeric columns that have not been normalized from categorical columns. So make sure your steps are correct in the correct order. And here we can see that we have one outcome variable, which is a price variable, and then we have all the rest of the variables, which add up to 9, which are the input variables. So let's go ahead and save this in data recipe, okay? And we can juice the recipe, which means, so here we've specified the preprocessing steps. We've specified the recipe, but we haven't actually implemented it. We haven't actually applied it to any data. So we can apply it to the training data set by using the juice function. And here, this is the result of the preprocessing. So you see how price is left untouched, but everything else has been normalized and vectorized. So we now have all these columns, and these have all been created from the original columns, and they have been converted into numbers, into numeric numbers, and they've been normalized and they've been vectorized, and it's just a perfect matrix of pure numbers that any machine learning algorithm is ready to consume